Okay, we're live for another episode in our open research series. This time we're going to be talking about prover decentralization, and we have our special guest, the OG wartime shitposter himself, Mr. Toghrul Maharramov. Welcome, man.
Hello, hello. Thanks for having me.
Yeah, thanks for coming on. Okay, so let's dive right into it. We usually like to make these like pretty dense and efficient. So to kick it off, let's set the stage. So how would you explain like what is a prover and what is its role in a ZK rollup? Like how does it contribute to this rollup process?
So a prover is a specialized entity that is responsible for computing proofs for the ZK rollup. So usually it'll be a Stark or a Snark proof that attests to the validity of the execution that was done for that rollup. So say like if a sequencer produces a block and we need to finalize it on chain, somebody needs to compute the proof for that block to be for that proof to be verified on chain and the block to be finalized. And that's the entity that does it in rollups.
Got it. Yeah, no, I think I'm sure a lot of people viewing this have a decent sense, but it's good to set the stage. So we're gonna pull up a tweet from you guys actually at Scroll, and the tweet talks about client diversity, Ethereum client diversity. So having multiple types of provers increase security. Can you actually break down the different types of provers there are?
So in this case, it just refers to any proof system. It talks more about the proof systems that are used by the provers rather than the provers themselves. So basically, the argument here is that the more proof systems you have attesting to the same state transition, the more secure the system is. So, for example, the way Scroll will work in the future currently doesn't work like that because the multi-provers don't live on the mainnet. Is instead of computing just one proof, we currently use a modified version of Halo 2. You would compute two different types of proofs. So currently we use SGX, which is a trusted enclave, and Halo 2. And we compute those two proofs, we publish them both on chain, and they're verified on chain. And if, let's say, they disagree for one reason or another, let's say there's a bug that someone is trying to exploit at one of the proofs, instead of what would happen if you have one proof, the bridge would just allow you to steal funds, for example, if the bug is severe enough. Whereas if you have two or more proofs, the chain will just halt. And that way you can prevent bugs inside proof systems to actually result in hacks that result in funds being stolen, etc., which is a big problem for provers because of their complexity and also because there are not a lot of people who can actually audit a zero knowledge proof circuit. I would say there are like a handful of people in the world, maybe not a handful, but like a few dozen people in the world who can actually audit a circuit, whereas like for example for us we have like thousands of lines of code that represents our circuits, which means that it's not just like looking at 5 lines of code and saying, oh yeah, it makes sense. It's like an extensive work, and therefore it makes sense to have multiple provers just to ensure that something isn't missed in one of the provers that results in a catastrophic failure.
Yeah, it's interesting because like it's not hard to intuit that having like that kind of redundancy, especially with like a really complex system, is a good thing. But I have to imagine that it introduces some other potentially such some complications, right? Like these provers are all like running at different like speed, like different like levels of like performance. Like obviously there could be like to what degree do they have to kind of synchronized, or are there any kind of like long tail of issues that people like us should worry about when trying to implement that type of prover diversity?
Yeah, there are a few things to consider here. One is the cost of computing the proofs. So let's say if you add a second prover that is extremely expensive compute a proof for, then essentially the transaction costs are going to go up, which is not ideal. Obviously, if your transaction costs are negligible and let's say you double the costs, then it's fine. But currently none of us have negligible transaction costs, which means that any additional costs will have a noticeable impact on the users who are transacting on Scroll. And another thing to consider is the efficiency of the prover. So basically, how fast it can compute the proof. Because let's say if you add a second prover that takes 5 hours to compute a proof, but your main prover takes like 5 minutes to compute the proof, then essentially your finality is bounded by the second prover, which is not great. Which results in like slower finalization and all the downstream effects of that, of like, oh, you need more prover capacity because you need to compute more proofs simultaneously, etc., etc. There are a lot of things to consider here. And on top of that, even on the mainnet, like even on your bridge, another consideration is how much cost does it increase to verify on top of the computation. So for example, with SGX, it's relatively not that expensive, but the problem with SGX is a bit different. For example, for us, the problem is that registering an attestation key for an SGX costs like a few million gas, which is not really sustainable if you want to rotate them on a constant basis. So that's one of the reasons why it hasn't been launched in the mainnet yet, because we're experimenting with different approaches of how you can basically amortize that cost to make sure that user transaction costs don't balloon just because you increase the security of the protocol.
Yeah, no, that's what I figured. I figured there are other things in addition to just the performance and like cost as well. I don't know how big of an issue these would be in practice, but I'm just like envisioning, you're relying on these two separate, like really complex systems, and maybe, like you said, there are not that many people who can like audit these at all, and just I wonder what kind of like practical implications there are where, maybe like you get some kind of like audit for one of them that takes a couple of months, but then the other one is delayed some extra number of months, and you're like, all right, fuck. It sounds like that's like not a very like interesting technical challenge, but just like a practical one.
Yeah, there are a lot of long tail side effects that you can have. Obviously, the assumption is that if you assume that the failure rate of all the proof systems is the same, then with a multi-prover, your liveness failure probability increases, it doubles. But the point is that the side effect of that, the positive side effect of that, is the probability of the correctness failure decreases drastically. And basically, if we were weighing the two, what would you prefer, a liveness failure or a correctness failure? Obviously, I'd rather have like an hour-long failure in block production than to have user funds stolen.
Yeah, totally. That I mean, I feel like just based on all like the Validiums that are launching, people feel similar to that across the space. So is two provers like the right way to go about this? Is there some other like flavors, like are people going to consider like 3 provers, 4 provers?
Yeah.
Like is it just is it that kind of thing where like more is better? Or I'm sure at some point there's a point of diminishing returns.
So basically the idea is this: an ideal, I think in my opinion, the ideal combination is having 3 provers. And the reason why that's the case is you would have 2 main provers that work in parallel and basically attest to everything. And then the third one acts as a tiebreaker in case there's a failure in one of the 2. And the advantage here is that in case there's this like failure in one of the proofs, instead of your liveness failing, you just use the tiebreaker to continue while you in the background fix one of the other primary proof systems that had the bug in it. And which means that you, assuming that the backup, the fallback, the tiebreaker doesn't fail as well, which is unlikely, that you have 2 different systems have bugs in them in parallel, you basically preserve your liveness and also retain that security of having multiple provers being functional in parallel, essentially.
What's your take on the following? What if instead of having multiple proofs, we just have one as the major proving system, and other two are used, for example, as a challenge proofs in case of some miscalculation or issues in the main proof? What's like the biggest issue, maybe except the confirmation time? Yeah.
So Taiko does that. So they have an SGX prover as the baseline prover, as the primary prover, and then they use ZK, I think it's Halo 2 for them as well, as the fallback prover. So how it works is basically that the T attests, and then there's a window, a challenge window. I don't know what it is. I think it's a few hours for them, within which anyone can submit a ZK proof to challenge the attestation of the SGX. But the problem there is, and I'm not saying that it's a big problem, but it is a trade-off in a way that you have to delay your finality, whereas with a multi-prover you don't, because they're just verified whenever they're ready, and then you finalize. Whereas in here you have to have this challenge window that allows people to basically compute a ZK proof and challenge it in case there's something wrong with the primary proof. But it's more cost effective, so it's a trade-off again.
Yeah, that's true. Agree.
So actually, we're going to pull up another tweet here. This time it's from Alana11 at Variant. And so basically Alana is asking, what should you decentralize first, the prover or sequencer? Curious to get your take on that. And you can kind of tie in like, not only like should one go before the other, but even like to what, how do you think about spacing them out? Is like one more important, like the super near term, like right when mainnet hits, like maybe you guys are trying to decentralize provers right now, but sequencing, you think, hey, that can wait a number of years. Is it bad to do them both at the same time? Like, how do you think about it?
So basically, you can divide this question into two different questions.
Yeah.
What is more important to decentralize, and what is easier to decentralize?
Sure.
So the prover is easier to decentralize. The sequencer is more difficult to decentralize, but the sequencer plays a more important role. So it's more important to decentralize the sequencer. And the reason why I'm saying that the prover is easier to decentralize is because even if you decentralize the prover and let's say there's a bug in your proof system, the prover cannot exploit that bug because the sequencer, in most of the designs, obviously you can have a design where that's not the case, the sequencer acts as a cushion in between the prover and the bridge. So like if the prover tries to exploit, like a malicious prover tries to exploit a bug in the proof system, a centralized sequencer will just reject it and not allow the funds to be stolen. Whereas if you have a decentralized prover and a decentralized sequencer, now that becomes a problem because now essentially a decentralized sequencer can collude with a decentralized prover if there's a bug in the proof system and exploit it.
Gotcha. And so, put yourselves in this. I mean, obviously, you're in the shoes of an L2 builder. Like, how, when should one be done versus when should the other be done?
I think in an ideal world, you would have both on day one, but obviously it's unlikely to be feasible in the foreseeable future. So I think just from implementation and complexity perspective, you should start with a prover because it's much easier to do and it doesn't have a lot of side effects. At least on a global scale. Obviously, it introduces complexity. Certain things become costly in terms of like the bridge, etc. But it's not as difficult to implement as sequencing. And when I say sequencing, I don't mean the decentralization itself, because one might say, oh yeah, you just slap Tendermint on top of your L2 and call it a day. That's it. And you can do that. But the security implications to that, as I mentioned before, because the decentralized sequencer is basically the gateway in between the bridge and provers and itself, if there's a bug either in the proof system or in the bridge, you're screwed. And so those implications are the ones that you need to be careful about.
Yeah, I was gonna ask the question, framing it exactly how you just said, like super left brain take. Like it's easy for people to be like, hey, like just slap Tendermint on it. Like we've decentralized.
Oh, yeah.
Cosmos is obviously like decentralized. You know, ordering in 100. I feel like each Cosmos chain has like 100 or so, or some of them have like 100 or so like validators. So it's easy to ask, just like, why is that so hard? But it sounds like there are other reasons why it's hard.
No, yeah, that part is easy. I mean, it'll probably take you a week to modify everything, maybe a bit more with the bridge and stuff to get it working. It's more about how do you build this like multi-layered defense against malicious sequencers once you become decentralized. Because if you're centralized as a team, you just obviously externally, it's up to each user to decide whether they want to trust you to be honest. But like we ourselves know that we're going to be honest. So there's no reason for us to like think about it that much. Whereas with decentralized sequencers, all of a sudden we don't have any control. And so essentially you need to make sure that that defense strategy is there in case something goes wrong.
Gotcha. Dimitri, how, what's your take on this? How are we thinking about it internally? I know it's obviously early days for us on DevNet, but maybe you can talk through our view.
So yeah, I can talk about my perspective, how I think about this. The first thing, my answer depends on the definition of decentralization, because as Toghrul mentioned, he's right. Decentralizing prover is easier comparing to sequencers, but the question is, what is decentralization actually? So if we define decentralization as some sort of trade-off between distribution and execution cost, then decentralizing provers are quite challenging task, because it may require some special hardware that can accelerate the computation that are quite limited. If you put everything into one data center, but all these computations are managed by different parties, does it mean that the system is decentralized or not? Because from one perspective, it's centralized, but it is trustless. So that is a bit tricky, I'd say. I think, of course, decentralizing sequencer is 10 times more important comparing to proving, because proving is a semi-solvable task. How to scale the proving, you just need to have some sort of it's very similar, by the way, to the mining that we had in the past, and we actually have this, for example, for Bitcoin today. But for sequencing, it's much more difficult, because you need to have a special consensus where you align on how to allocate slots, how to make sure that your ordering is correct, and etc. So it's quite complicated research task to do. So of course, sequencing is much more important.
Yeah, and just to add here, as Dimitri said, sequencing is more important because it just ensures more properties. So with proving, the only thing that you're realistically trying to achieve is maximizing liveness guarantees. Because let's say if there's a centralized prover and goes offline, that's it. You have to wait for that prover to come back. Whereas with sequencing, you have a few properties that you are ensuring. You're ensuring real-time censorship resistance, you're ensuring real-time liveness, and you're also trying to provide strong economic pre-confirmation guarantees, which are much more noticeable to users. Because another thing to consider here is that even if a prover goes offline, your chain still continues to function. You can just not finalize it on chain. So for users transacting on your chain who are not withdrawing funds, nothing changes. And so it has a significantly milder impact on the UX, at least short term, after the failure. But of course, it's still important to have it decentralized at the end of the day.
I'd say also it is important because so if we try to model the attack vector for both of these topics, let's say, then the equation of the value you can extract comparing to the cost of attack, for example, for proving is much more higher comparing for sequencer, for example. So from this perspective, from optimizing the vulnerable parts, it's more important to protect sequencer comparing to the proving layer.
Right. Do you see other dynamics coming in and influencing the priority here? Like, so for example, like at least as far as sequencing goes, you hear a lot of like regulatory concerns, and that might influence a team to kind of move faster on that. But even like on the, I'm thinking more about like on the proving side, you just mentioned UX and users. I mean, is one of them worth prioritizing because it's more of a competitive edge for devs or users? Like, how do those practicalities tie in?
Yeah, of course, there are different things that you need to consider here in terms of regulatory pressure and stuff. I guess if there's a scenario in which there's significant regulatory pressure to decentralize, then obviously the teams will prefer to decentralize the sequencer first because there's more liability when you operate the sequencer yourself. In terms of UX, as I said, I think again sequencing is more important in terms of the UX because a failure of a sequencer or a censorship of a sequencer has more direct and like real-time impact on UX versus something like proving. But I think in general, I see a lot of the teams, they're probably going to decentralize proving first, precisely because it's just easier. So, and also it's a good way to basically introduce gradual decentralization versus just like saying we're like turning on the switch, off the switch in one day and just saying, yeah, completely like you're in complete control, because it's likely that the same people who are operating the decentralized provers are also going to be willing to operate decentralized sequencers. In fact, from our perspective, the current leading design is combining, essentially decentralizing the provers first, and then combining the prover and the sequencer role into one, and having this like mega entity that does both sequencing and proving do both at the same time, which means that by decentralizing proving first, we're easing in the system into eventual full decentralization.
Actually, can you talk a little bit more about that? I think I've seen a couple hot takes from you on it, but I don't know if you've expanded upon it. Actually, I haven't gotten around to reading your latest article. I'm not sure if that's mentioned in there, but anyway, yeah. Can you just expand upon like why combine these roles?
The reason why you would want to combine these roles are a few. One, it reduces complexity. If you have multiple roles running in parallel, especially if you have staking, that means that you have to handle staking for both roles, etc. It's just not a very clean and easy system to build. And two is the incentives part. So let's assume that the majority of the value captured by the L2, at least in the foreseeable future, once we decentralize, is going to be MEV. It's likely that sequencers are just going to outsource block construction to some trusted entities that are specializing in maximizing value extracted per block. Well, at that point, the sequencer is just a middleman between the builder and the prover. So why not just remove the sequencer and have the builder communicate directly with the prover? And on top of that, that also solves another problem of how do you distribute incentives, because the cost of proving is much higher than operating a sequencer. So you would want the majority of the value to go to the provers. Two, you want more provers than you want sequencers, because as long as you have, let's say, like a few dozen sequencers, that's good enough. Whereas for provers, essentially, in a way, you're proving your throughput, assuming that there are no other bottlenecks, your throughput of the chain scales with the number of provers that you have in the system. So the more provers you have, the bigger throughput you can handle without delaying finality. And therefore, you want those incentives to go to the provers, but because the sequencers control the ordering, they get to absorb most of the value, which means that you have to either design an auction system or somehow hard code the separation between the revenue to ensure that the provers are incentivized sufficiently, which is just like an unnecessary complexity to have, and it just makes more sense to have one role to avoid that complexity.
Dimitri, what are your thoughts on that?
I don't know what to add here.
No, I mean, it seems completely reasonable. That resonated with me.
And I think just to add there, I think it's not just us thinking about that. I think Starkware is 100% moving towards the same design. And as far as I remember, I haven't checked the latest documentation, but Aztec is also considering doing that instead of just having two separate roles. Of course, if you have base rollups, then you don't really have an option. You should have two roles, but then, and that's one of the reasons why I'm against base rollups, specifically for ZK rollups. Base sequencing, I mean, is primarily because of that incentive problem of like, how do you ensure that the provers get the majority of the value accrued?
So the problem is partially solved by using, for example, optimistic ZK, where you have like challenges, and for challenges you pay additional fee. So from this perspective, it's not the biggest problem. But I'm curious about maybe the thing that might be much more interesting. For example, how to differentiate role, the relay role, and for example, sequencer role. Because from the value threshold, these roles can be super different in terms of the amount of value they serve to the system. And I'm a bit skeptical here, because splitting roles sometimes may be dangerous. Sometimes, if you don't have enough guarantees that ensures the equality of the value for the roles. The nice take was about base rollups. For them, it really can work, because you manage all your input transactions from layer one, and from this perspective, you can easily combine these two roles. But actually, I think it requires some like good calculations of the model of the value model, and to calculate estimate potential risks here. But yeah, that's a nice thing to that's a nice thing to think here.
Toghrul, you had mentioned before we actually jumped on a number of other aspects of prover decentralization. I don't know if you want to share like slides and talk about them. Maybe you could just expand on some of that.
Yeah. So another thing that needs to be considered here is, obviously, if you naively build a ZK rollup and just ignore all the optimizations, etc., your system is likely to have a model in which proving happens sequentially, which means that like a prover computes a proof for one block. Once that proof is computed, the same prover or another prover computes a proof for the next block, etc. But the problem, at least right now, obviously once we have real-time proofs, that's no longer a problem, is that if you do that, then essentially your finality scales super linearly with your block times. because currently proof times are longer than block time. So let's say if your block is produced once every 3 seconds, but your proof for that block takes 5 minutes to compute, just imagine how that scales super linearly if you're just sequentially computing the proofs. So the solution to that would be pipelining, is essentially having different provers. In a centralized system, you're abstracting away basically from an external user. It seems that there's one prover, but you just operate multiple machines. In a decentralized system, it's more transparent, so the smart contract will handle it. And basically, the validating bridge on the L1. And basically, you would assign different provers to different slots, and then basically one prover would wait. Instead of waiting for the other proof for the previous block to be computed, they will compute them in parallel. Because once you have a block, there's no dependency on another proof. You can compute them in parallel because it's deterministic. And at the end of the day, you would have an aggregator that combines, let's say, 100 of those proofs, and then aggregates them into one mega proof and then publishes it on chain, which basically reduces your time, because now instead of the super linear relationship where essentially your proof time scales by multiplying the block time by the number of blocks that you're computing, now it scales almost linearly, which means that basically there's a small delay, but it's near constant, basically, assuming that, like, let's say a certain prover doesn't fail to submit a proof in time, but then you can have fallbacks, etc., and that's fine.
So this proof pipelining, I think you mentioned a couple of other things too offline. I don't know if it was prover marketplaces.
No, we can talk about that as well. I think the other thing that I mentioned, and that has been a gripe of mine for a long time, is basically a lot of people think that you can use proofing to emulate work that is done in classic Nakamoto consensus with proof of work, such as Bitcoin, where essentially you have the entire network competing with one another to solve the cryptographic puzzle. And people think that you can emulate it in ZK. But the problem there is this. And in something like Bitcoin, the probability of you solving the cryptographic puzzle is equivalent to the hash rate relative to the total hash rate that you control, so the percentage that you control. Whereas in a system like, assuming that everything else is synchronous, whereas in a system like rollups, CK rollups, for example, the problem here, without introducing any randomness, the fastest prover always wins, which means that the long tail effect of that is that it's extremely centralizing, because if the fastest prover, or let's say the fastest two provers, always win, that means that there's no incentive for everybody else to compute proofs and waste their energy and pay money for for operating those provers, which means that you end up with a system that is extremely centralized long term, and that's just not a good design. Obviously, you can play around and add randomness, etc., to make sure that it's more fair, but even then, I don't see a reason why you would do that, because that would be extremely wasteful. Because you would, let's say, in a system where you have thousands of provers functioning, you would have all of them compute the proof, instead of having them pipelining and computing different proofs, which is like, one, you would need to subsidize them more, which means that the cost per transaction would be more if they're competing, and two, the finality is going to be much slower, even if we assume that the proof time is shorter than the block time.
Yeah, that makes sense. Okay, so we're coming up on time. I definitely want to get your take on like proof marketplaces and some of the other like proving products that are popping up. and then we're gonna finish. And obviously, if there's anything else that we missed that you think we should talk about, by all means. But then we're gonna wrap up with a little lightning round mini game. So let's start with proving marketplaces.
Yeah, I think there are multiple reasons why you would want to have marketplaces. One is we're getting to a point where, even though it's not the case right now, I think soon enough the underlying technology is going to converge, meaning that the hardware specs used by different proofs by different ZK rollups are not going to be that different, because right now Polygon, for example, is optimized for CPUs, and our prover is optimized for GPUs, which means that our provers are not directly compatible with one another. And for example, like different provers have different RAM requirements, etc. We, for example, use 250 gigabytes of RAM for a prover, then somebody else can use even a terabyte of RAM, etc. So the hardware differs, and therefore it's difficult for you to actually lend your capacity to others when you're idle, because in a system where you have pipelining, you have to have a certain number of provers idling, waiting in case there's a fallback necessary. And so you can always maximize the revenue by basically participating in a prover network and lending your capacity while you're idling, which means that you essentially you're not wasting your hardware just sitting around doing nothing. And then on top of that, because as I mentioned previously, because the systems are obviously assuming that there are no other bottlenecks, your throughput is bottlenecked by the number of provers. Even if you build a decentralized network, you have a fixed number of provers participating at any one time, which means that in case there's a spike in the demand, you either have to expand the number of provers, or you can let those provers outsource proofs to a prover network, which means that the prover network or the prover marketplaces act like almost like on-demand services that you can tap into in case there's like more demand, the capacity internally available within your prover network. And then on top of that, you can also think about the SDK. So let's say if you spin up your own, let's say ZK OP stack ZK chain with succinct, and you don't want to handle the infrastructure internally and run all the provers, etc., but you want to be decentralized, then you would outsource it to some marketplace to do it for you. So there are multiple uses where like marketplaces are useful and potentially even important for certain use cases.
Before we wrap up with this mini game, Dimitri, was there anything else that you wanted to discuss? And Toghrul, was there anything we missed?
No, I think we're good.
Yeah, same from my side. I think we chatted about most of this stuff.
All right, boys, we're gonna do a rapid fire round. This is just a little fun experiment. I'm gonna have both of you answer very quickly, yes or no questions. And let's go Toghrul then Dimitri. So, are you ready?
Yeah.
Yeah.
All right. Will ZK rollups completely replace optimistic rollups in the next 5 years?
Yes.
I think yes.
Will ZK proving costs become negligible within 10 years?
Yes.
It depends how you define.
Yeah, obviously it depends on how you define negligible.
Because it's quite unfair to compare, for example, achievements that ZK can achieve in 10 years comparing to CPU, for example, computations, because what we're trying to prove is what humanity achieved in the last like 50 years. and they build extremely optimized hardware for this. And I don't think we can achieve something feasible in 10 years. It can take like 30 years easily to achieve a feasible performance to get like at least 1000% performance decrease comparing, for example, to regular computations.
So, Dmitry, but your assumption, sorry, it's not a very rapid fire session.
You're good. Go. No,
I think you're right only if you assume hardware improvements, but I'm also assuming the proof system improvements as well. Because if you look at how far we came in the last 5 to 10 years, it's been an incredible improvement in terms of in terms of prover efficiency. And so I think if you combine both, I think I wouldn't put it past this industry to basically reach a point where proving costs are negligible. And like negligible, you can argue that they're negligible now because proving per transaction is like sub-cent. But I mean negligible isn't like a fraction of a cent.
Okay, so if your proving cost is 10 times more expensive comparing to execution cost, does it mean that you achieve the goal or not? Because,
I don't know.
If your computation cost of serving a sequencer is 30K per month, for example, then the proving cost is 300K per month.
Yeah, that's fair.
So it's more, I think, value specific, and it depends how you wrap the value of your specific needs. And only by defining your personal constraints for the product and for community, I say, only by doing this, you can say, do you achieve the goal or not?
This is the longest rapid fire session in history.
Oh, these guys brought nuance to the rapid fire. All right, no, this is good, but we press on. Okay, is Ethereum's move to proof of stake the best decision it ever made?
I think yes. I don't think it's maybe the best decision they have ever made. I think adding native event logs for native transfers is more important, but it definitely was a very important decision.
I would say yes.
Will there be more rollups or validiums on Ethereum in the long term?
Rollups.
I think rollups.
This is obviously not a yes or no question, but which one?
Yeah, because like it's only the matter of how you improve your DA systems, and it definitely will improve like within like several years. So it won't be a problem. You won't need to have validiums anymore.
But I also think that people who think that there are going to be thousands of rollups are wrong, and I think the majority of the capacity is going to concentrate on a handful of rollups, and then you might have a long tail set of like app specific or like very, very community specific, let's put it this way, for a certain use case rollups, even though they're generalized.
I see. So like, let's go on this detour for a second. Because your first reaction of there won't be that many rollups, I was going to like contest that because I think there will, but you're saying that there won't be that many just purely general purpose rollups that are supporting all types of applications. But whether or not like there are technically general purpose rollups, you think there will be a long tail that focus on specific use cases or apps or verticals or whatever. Okay.
Yeah.
Got it. All right. Have you ever fallen asleep during a conference or a talk or a space?
Yeah, probably.
You don't remember?
Yeah, I don't remember. I was asleep.
Definitely yes. If you don't remember.
I'll look for the evidence. All right. And finally, are trustless bridges real?
No.
It depends on the definition.
No. It doesn't matter what the definition, they're not real.
Are you sure, man? Because there's so many people claiming on Twitter that they have these trustless bridges, and I feel like they probably do, right, Toghrul?
You know, I love the LTB guys. I'm good friends with quite a few of them, but I hate them for one reason only. I gave a really long talk last year at their event in Warsaw that was recorded, but they never published any of the talks from that conference. So whenever people start talking about trustless bridges, ideally I would like to just link them to that talk, but like it's not live, so I have to write this whole spiel on Twitter every time somebody claims that they have a trustless bridge.
You've actually been shipping a number of articles recently. Maybe that's the next one.
No, that'll take too much time, because you have to like go into the philosophy of like is sharding, bridging, etc. And it's just like,
yeah. So we'll stick to a hard no for is our trustless bridges real. All right, guys, let's wrap up. Thank you so much, Toghrul, for coming on, man. This is always good to chat, and this is definitely very informative.
thanks for having me.
All right, sounds good. And thanks everybody for listening who made it this far. And we'll have another episode next week. All right, see you guys.
All right, guys. See ya.